I have a proposition for you today that might sound a little, well, wild,
Okay,
or maybe just painfully nostalgic for some of us.
I'm intrigued.
I want you to cast your mind back um, to being 6 years old. You're sitting at one of those little laminate desks.
Yeah, the ones where the chairs are attached.
Exactly. Maybe you've got a really dull pencil in your hand, and there is a worksheet in front of you. You are learning to add 2 plus 2.
Right.
It feels simple, right? It feels like the absolute basics.
This is the universal experience. We all think of it as just learning to count.
Exactly. But what if I told you that first grade math isn't just about, learning to count to 100 or stacking numbers on top of each other?
Uh-huh.
What if I told you that what's actually happening in that 6-year-old brain is the absolute foundation for high-level algebra and complex problem solving?
That's a bold claim.
Right. And here's the kicker. What if the way most of us were taught actually installs these bugs in our mental programming that mess us up years later?
See, it's not a wild proposition at all, really. You look closely at the pedagogy. First grade is where the code of mathematics is either cracked or it's completely scrambled for life.
So to help us decode this, we are doing a deep dive into a really fascinating document today. It's titled Focus in Grade 1.
It is a great text.
It really is. It's a pedagogical text that breaks down the number and operations core. Now, before you tune out thinking we're just reviewing a teacher's manual,
Which we are not.
we are definitely not. We are looking at the hidden logic, the source code behind how humans actually learn numbers.
And honestly, we're looking at why English speakers specifically are at a massive disadvantage.
Yes, that is the part that really grabbed me.
Yeah.
Our mission today is to uncover why the English language actually makes math harder for kids.
Right.
Why most of us completely misunderstand the equal sign, and why the way we were taught to stack numbers, vertical addition.
The vertical trap.
Right, why that
Yeah.
might actually be a massive trap.
Correct.
It really is a trap that leads to specific errors that teachers see constantly in second, third grade. But we really have to start with the immediate hurdle, which is the language itself.
Okay, let's unpack this. Because the source material points out that the biggest headache for English-speaking children is the teen numbers.
Oh, absolutely.
Basically 11 through 19. Why is this such a disaster zone?
Well, it comes down to regularity. The human brain is essentially a pattern recognition machine.
Sure.
In mathematics, patterns allow for prediction and understanding. If you look at many East Asian languages, Chinese, Japanese, Korean,
Okay.
the number system is perfectly regular.
What do you mean by regular?
For example, the word for 11 translates literally to 10-1.
Oh, wow.
Right. 12 is 10-2, 20 is 2-10.
That makes so much sense. You literally hear the value in the name. 10-1.
Exactly.
You visualize a group of 10 and a 1 immediately.
Precisely. The language reinforces the math. But in English,
It's a mess.
it is. We have 11 and 12. These are arbitrary words. They don't sound like 10-1 or 10-2.
No, they sound like elf names.
Right. They are historically derived, sure, but to a 6-year-old, they're just random sounds they have to memorize, like table or chair.
They don't carry any numerical information at all.
None. And then you get to 13 and 15.
Right, because we don't say 3-teen or 5-teen.
Exactly. We completely mask the root numbers.
And then there is the reversal issue.
Oh, the reversal issue.
Wow.
This is the part that really trips up the cognitive processing.
This blew my mind. Okay, so imagine a kid writing the number 14.
Okay.
They write the 1 first.
Right, which represents the 10.
Exactly. And then they write the 4, which represents the 1s.
But when we say it,
We say 14. We say the 1s first.
it creates a massive cognitive disconnect. You are asking a child to map a sound to a symbol, but the order is entirely flipped.
It's completely backward.
In German, this reversal continues all the way to 99, so at least it's consistent.
That's true.
But English teases you. We reverse the teams, saying the 1s first, but then when we hit 20, we switch back to saying the 10s first.
21.
Right. It's bait and switch.
Just when the kid thinks they've found the pattern, we change the rules.
Exactly. It creates a huge barrier to understanding place value.
Yeah.
The child hears 4 first, so they naturally want to write the 4 first.
I mean, I would too.
It takes a lot of mental energy to suppress that impulse and write the 1 first.
So how do we fix this? The source material talks about a specific tool called secret code cards,
Yes.
which sounds like spycraft, but it's actually for math. How do these work to fix the language bug?
It's a brilliant way to visualize the hidden 0. So imagine you have a card that says 10. a 1 and a 0.
Okay, got it.
The 0 is on the right. Then you have a smaller card with a single digit, say an 8.
Right.
To make 18, you place the 8 physically over the 0 on the 10 card.
So visually, it looks like 1-8. It looks like the number 18 we all know.
Correct. But here is the aha moment. You can peel that 8 away and reveal the 0 hiding underneath.
That's clever.
It proves to the child that 18 isn't just a 1 and an 8 sitting next to each other like neighbors on a bus.
Right. It's not just two independent digits.
It is a 10 and an 8. The 10 is still there, existing as a value, just covered up.
That is so much better than just writing it on a whiteboard. It makes the place value physical.
Yes.
It's almost like object permanence for numbers.
That's a really great way to put it.
Yeah.
And the text pairs this with something called 5 groups.
Right, I saw that.
This is another visualization tool to help kids break away from just counting by ones forever.
This is like the patterns on dice, right?
Yes, exactly. If you see the 5 dots on a die, you don't count 1, 2, 3, 4, 5.
No, you just know it's 5.
You just see 5. That's called subitizing.
Huh.
5 groups use that instant recognition.
Okay.
It helps kids see that numbers like 6, 7, 8, and 9 are just a 5 group plus some extras.
So a 7 is just a 5 and a 2.
Right. It anchors their understanding of quantity, so they aren't constantly starting from 1 for every single calculation.
Which brings us to the next big segment, and this is the one that really sold me on the idea that first graders are essentially doing pre-algebra.
It's true.
We need to talk about the equals sign.
This is probably one of the most persistent misconceptions in all of education.
I am completely guilty of this. If I see 2 + 2 = my brain just screams the answer is 4.
Right.
It feels like the equals sign is a button you press to get a result, like on a calculator.
And that is exactly what we need to unteach. The source emphasizes that children, and clearly many adults,
I know.
view the equal sign as an operator. They think it's a command to do the work or put the answer here.
Yeah, that's exactly how it feels.
But algebraically, the equal sign doesn't mean calculate. It means is the same as it represents balance.
So if a kid only sees equations where the operation is on the left and the answer is on the right, like 5 + 1 = 6?
They get completely confused when they see algebra later on.
Because algebra mixes it all up.
Exactly. If you present a first grader with 6 = 5 + 1,
They think it's broken.
many will say it's outright wrong because the answer is on the wrong side. They think the equation is flowing backwards.
Wow.
The text suggests that to prevent high school algebra struggles, we actually must expose 6-year-olds to equations where the single number is on the left.
So they need to see that 6 is the same as 5 + 1.
Yes, it builds that concept of equivalence early.
This leads to the concept of partners. I love this terminology. It makes numbers feel like they have relationships.
It's the decomposition of numbers. A number like 6 isn't just a solid, unchangeable block.
Right.
It has partners hiding inside it. 5 and 1 are partners that make 6. 4 and 2 are partners. 3 and 3 are partners.
And this isn't just a cute naming convention. This is the commutative property in disguise.
Right. Through playing with these partners, they learn what the text calls partner switches.
Okay.
If you know that 4 and 2 make 6, you also discover pretty quickly that 2 and 4 make 6.
So they realize early on that in addition, order doesn't matter.
Exactly. That is a fundamental algebraic concept, and they are grasping it through simple decomposition before they can even read a chapter book.
That is amazing. So we've got the structure of the numbers, the partners, the balance. Now let's talk about the actual act of adding.
The mechanics of it.
Yeah. The source outlines this fascinating evolution of how a child's brain processes a problem like 8 + 6.
Right.
It's not just getting the answer. There are distinct levels of thinking here.
It is a progression of efficiency.
Yeah.
Level 1 is what we call counting all.
Okay, so how does that work for 8 + 6?
So the child puts out 8 physical items. Then they put out 6 items. Then they go back to the very beginning and count every single item starting from 1.
1, 2, 3. All the way to 14.
Exactly.
Which works. It gets you the right answer.
It does. But it's incredibly slow, and it's very prone to error if you get distracted.
I would definitely lose count.
Most kids do.
Okay.
So the major cognitive leap is level 2, which is called counting on.
Counting on.
This is where the child holds the number 8 in their head and then counts forward 6 times.
Yeah.
9, 10, 11, 12, 13, 14.
That sounds simple to us, but the text mentions that this is actually really hard for a kid. Why is counting on such a hurdle?
It's because of the double meaning of the number 8.
Double meaning.
This is a very subtle point. In level 1, 8 meant a set of 8 physical objects, a cardinal meaning.
Like here is a pile of 8 things.
Exactly. But in level 2, 8 becomes a starting point in a sequence, an abstract location.
Oh, I see. It switches from being stuff to being a place on the list.
Exactly. The child has to switch from thinking of 8 as a concrete pile to 8 as an ordinal position, and then start counting the next 6 numbers.
That abstraction is a really heavy lift for a 6-year-old brain.
It is a massive developmental milestone.
And I have to bring this up because the text defends it. Fingers.
Oh, yes?
I feel like fingers get such a bad rap in math class. Teachers are always saying, put your hands away, don't use your fingers.
They do. But the source clarifies that fingers are completely fine.
Really?
In counting on, fingers are a valid tool for keeping track of that second addend.
Makes sense.
If you are starting at 8 and counting on 6, you need to know when you've actually counted 6 steps.
Otherwise, you just keep counting forever.
Right. Using your fingers to track those 6 steps allows your brain to focus on the number sequence itself. It's not a crutch. It's working memory support.
I love that. Free the fingers. But obviously, we don't want them doing that when they're 20.
Well,
What is the final level?
Level 3 is the Make a 10 method.
Make a 10.
This is very common in East Asian math pedagogy, and it is the most efficient mental strategy. For 8 plus 6, the child actually doesn't count at all.
Wait, no counted.
No counting. They look at the 8 and think, I need 2 to make a 10.
Okay.
So they mentally take that 2 from the 6.
So the 8 becomes a 10, and the 6, having lost 2, becomes a 4.
Exactly. So the problem 8 plus 6 instantly transforms into 10 plus 4.
Wow.
And because of our place value system, we know 10 plus 4 is 14. Instantly. No counting required.
It just snaps together.
It relies on deep fluency with those number partners we discussed earlier.
That is sleek. That is the kind of mental math that makes adults look like wizards.
It really is.
But to get there, we have to avoid some traps. And this section of the source material was honestly shocking to me. There is a warning about vertical addition.
The vertical trap. This is a big one.
Yeah. I mean, we all learned to stack numbers. 58 on top of 36. Draw a line. Add the columns. Why does the text say this is dangerous in first grade?
The danger is that it destroys the child's sense of place value.
How so?
When a child sees 58 stacked over 36, and they are taught to just add the columns, they stop seeing 58.
What do they see?
They just see a 5 and a 3 in one column and an 8 and a 6 in the other. They treat it as 2 separate single-digit addition problems.
So they aren't adding 50 and 30, they are just adding 5 and 3.
Correct. And while that gets the right answer for addition...
Which is why we think it works.
Right. But it leads to a very specific, disastrous error in subtraction later on.
Oh, no.
Imagine a subtraction problem. 52 minus 38, written vertically.
Wait, 52 on top.
The child looks at the ones column. 2 on top, 8 on bottom.
And they think, I can't take 8 from 2.
Right. So what do? If they view these as isolated columns, they just subtract upwards.
Wait, they just go 8 minus 2?
Yes. 8 minus 2 equals 6. They write down 6.
Because they've been trained that columns are just isolated single-digit problems, they don't realize they can decompose the 50 to get more ones.
Exactly. They don't understand the whole number anymore. So the concept of borrowing makes absolutely no sense to them.
That is terrifyingly logical. So how do we fix this?
To fix this, the source suggests math drawings.
Like drawing sticks for 10s and dots for 1s.
Yes. Or writing problems horizontally for much, much longer. Writing 58 plus 36 in a single line.
That makes total sense. If you write it sideways, you can't just line up the digits blindly. You have to deal with the 50 as a 50.
It forces the child to recognize the whole value.
Now, another sacred cow, the text slaughters, the number line.
Yes. The text argues that number lines are actually too abstract for first graders.
But I see number lines in every classroom. They are literally taped to the desks.
You do. But think about how a child uses a ruler or a number line. It's a length model.
Oh, okay.
If you tell them to start at 0 and move 3 spaces, they often count the hash marks.
Right.
They count the 0 hash mark as 1.
Oh, right. And then they end up 1 short of where they should be.
Exactly. It's an off by 1 error because they're counted the marks, not the intervals or spaces between them.
The space is the actual number.
Intervals are invisible concepts. Hash marks are visible things. Kids count things.
So what's the alternative? Do we just ditch the tape on the desk?
The alternative is a number path. Think of it like a board game track, like Candyland.
Oh, where you jump from square to square.
Exactly. You have a track of squares. You're counting the actual spaces or objects. It's a count model, not a length model. It's much more intuitive for a 6-year-old brain.
It's subtle, but I can totally see how counting lines versus counting spaces would trip a kid up. One last trap before I move on. Keywords.
Oh boy.
Teachers love these. If you see the word more, it means add. If you see fewer, it means subtract.
This is a major pitfall. It completely stops critical thinking.
How so?
The source gives the example of comparison problems, which are the hardest type of word problem. Consider the sentence, Ali has 4 fewer balloons than Lisa.
Okay, I see fewer, so my brain immediately wants to subtract.
Right. But what if the question is, if Ali has 9 balloons, how many does Lisa have?
Wait, let me think. If Ollie has 4 fewer, that means Lisa has more?
Yes.
So I actually have to add the 4 to Ollie's 9 to find Lisa's total.
Exactly. Despite the word fewer, you have to add. If a child has been taught that fewer always means subtraction, they will fail this problem every single time.
Because they aren't reading the problem, they're just hunting for the keyword.
We have to teach them to simulate the actual situation in their head, not just scan for shortcuts.
That is tricky. You really have to visualize the balloons.
You do.
Speaking of visualizing, let's talk about money. The source brings up a point that I honestly never really thought about. Coins are completely illogical to a child.
Visually, they are a mess.
Right. A dime is the smallest coin, yet it is worth more than the nickel and the penny, which are physically larger.
It contradicts a child's natural logic that bigger means more.
So how do we explain that a tiny silver coin is worth 10 big brown ones?
The source suggests using dime strips and nickel strips.
What are those?
Imagine a strip of paper with 10 pennies drawn on the back. On the front, it's a picture of a dime.
Oh, I see. It links the value directly to the quantity.
Yes, you can physically see that the dime strip is the same length or value as 10 individual pennies.
That's a great bridge. But is teaching money just about buying things?
Not at all. The real power of money in first grade is about place value fluency and what we call unitizing.
Unitizing.
When you count mixed coins, you are doing mental gymnastics. You count dimes,
Yeah.
10, 20, 30.
Yeah.
Then you hit a nickel. You have to stop, shift gears, and count by fives. 35, 40.
And then a penny, 41, 42.
Exactly. That shift from tens to fives to ones is the code of place value right there,
It forces the brain to organize quantities into different unit sizes.
which is exactly what you need for multi-digit addition later. You're building the flexibility to switch between units rapidly.
Wow. So what does this all mean? When we look at all these pieces, the secret code cards, the partner numbers, the dime strips, it seems like the theme is looking beneath the surface.
The source actually calls it mathematizing.
Mathematizing, I like that.
It's about teaching a child to see the underlying structure in the world, not just to count objects. It's moving from I see 3 apples and 2 apples to understanding the abstract relationship that 3 plus 2 is a constituent part of 5.
It's a profound shift in worldview.
It really is.
It gives me a whole new respect for first grade teachers. They aren't just babysitting, they are literally wiring the logic centers of the brain.
Absolutely. And before we go, I want to leave you with one final provocation from the text.
Okay, hit me.
It challenges the way almost every single adult in the U.S. learned to add.
Oh, I am ready for this.
It's about where you put the new 10.
The new 10, you mean carrying the 1.
Yes. You know when you add 58 plus 36, you add 8 and 6 to get 14. Standard procedure is to write the 4 at the bottom and carry the 1 to the top of the tens column.
Right, the little one floating above the 5. That's how I do it. That's how I've done it my whole life.
The source suggests a method called new groups below.
New groups below, how does that work?
Instead of carrying the 1 all the way to the top, you write the new 10 below the answer line in the tens column.
Wait, why? Does it actually matter where it goes?
It actually does. 2 big reasons. First, when you write the answer 14, you generally write the 1, then the 4.
Yeah.
If you carry the 1 to the top, you are physically writing the 4, then moving your hand way up to write the 1. You're splitting the number apart across the entire vertical space of the problem.
Oh, true.
If you write the new 10 below the 4, you can still see the 14 sitting there vertically.
Oh, I see. The 1 and 4 are closer together. It preserves the actual number.
Yes. And second, when you add the tens column, it's easier to see the numbers you started with, the 50 and the 30. You add them to get 80, and then you add the new 10 waiting at the bottom.
It reduces cognitive load.
Exactly. You don't have to hold the carried number in your head while adding the other 2.
That is fascinating. New groups below, it feels so minor, but I can totally see how it helps keep the logic intact.
It makes a huge difference for learners.
I'm going to try that the next time I have to scribble a math problem on a napkin.
It might just save you a mistake. And it definitely respects the logic of the numbers more than the traditional way.
Well, there you have it. First grade math. Deeper, weirder, and way more logical than you remember.
Definitely.
It turns out we weren't just learning to count, we were learning in the language. Next time you're calculating a tip or adding up a score, try to find the partners in the numbers. You might just surprise yourself. Thanks for listening to this deep dive.
Keep learning.